Welcome back, Grade 6, to Nelson Math, Chapter 11, Getting Started. Let's do a bit of review from previous knowledge. So we are going to calculate the area of each polygon. I'm going to start off with B, and you'll see why in just a second. So right here for B, we know that our formula for this is the length times the height, or the length times the width, or whatever you want to call this dimension, multiplied by this dimension. This is using the array model. So imagine that you have this rectangle being made up all of centimeter cubes or centimeter flats that are 1 centimeter by 1 centimeter. We would have 24 of these cubes or flats in here. So that's 4 times 6. Now I'm going to go back to 1a. So if we look at this one right here, this is exactly half of a rectangle. If I imagine that there was a rectangle here, the formula for this would be, for the area, would be 2 times 5, and that would be 10 centimeters squared. However, we are not finding the area of the whole rectangle. We want exactly half the rectangle, which gives us this triangle. So if the area of the rectangle is 10 centimeters squared, the area of the triangle must be exactly half of that. In other words, 5 centimeters squared. Let's go on to C now. On C, or for the letter C, we have exactly half of a parallelogram. If I copied this exactly and copied it over onto this side, I would end up with a parallelogram with a base of 5 and a height of 3. So the area of the parallelogram would be 15 centimeters squared. But I want half of the parallelogram, which is half of 15. In other words, 7.5 centimeters squared. And here's D. D, the area of a square, is just side times side. You could call this side squared or length times width. And the area is 49 centimeters squared. For number 2, it's asking for the volume. The volume is different than area. They are related, but they are definitely different. Volume we measure with cubes like this. Notice it is three-dimensional. It has a height, a length, and a width, whereas these polygons here only have a height and a base, or a height and a length, or a width and a length, only two dimensions. So it's asking for the volume of each cube structure. Let's look at 2a. For 2a, we could use a formula, or we could count the cubes. So let's count the cubes in an organized way, starting from the top layer. The top layer, I could count them one by one, or I could use the information I know about multiplication. I have in every row this way, I have 1, 2, 3 cubes. But now I'm going to count how many rows this way I have. 1, 2, 3, 4, 5. So in my top row, I have a 3 by 5 number of cubes. So 3 by 5 for the top row is 15 centimeters cubed, because I have 15 of these cubes. Now let's look at the bottom row. It happens to be exactly the same. We do have to make a little bit of making inferences here and inferring, because we can't see every single cube in the bottom row. There could, for example, be 3 missing in the bottom row that we just can't see. However, we're going on the assumption that it is a full entire layer. So the bottom also has 15 centimeters cubed. That means we have a total of 30 centimeters cubed. We could have also used the formula here, the formula you've previously learned, which would be height times width times length. And that would give us, if we were to count them, 2 times 3 times 5. So if I did 2 times 3 times 5, we would end up getting exactly the same. So 2 times 3 is 6 times 5 is 30 centimeters cubed. That works no problem if we chose to do it that way. For the letter B, it's similar, not the same, but similar. Let's start once again at the top. On our top row, we have 3 by 3, so that would give us 9 centimeters cubed. Beneath that, we have another row that we are going to assume is exactly the same as the top layer. So that's another 3 by 3, and that would be 9 centimeters cubed. And on the bottom, it may be hard to tell, but there are only 4 cubes supporting the whole structure that we can tell. In this very front part of our last layer, we see there's one missing in the middle. If we look in our second row, we see there's one missing on the left, one missing in the center, and one missing on the right. So there are 0 there. And at the back, we can't see the whole back. We know that there's one in the back left corner, there's one in the back right corner, but we can't see anything else. And we are going to make an inference here that there are only 2 at the very back. That means our lowest layer only has 4 centimeters cubed. So if we add these up, we could say 9 plus 9 is 18, plus 2 is 22 centimeters cubed. Now, if we made a different choice and we justified it by stating what our options might be, we could have, for example, stated in the third layer, there is an entire back row, in which case I could have added another one and said there are 5 in the back row. I can't know for sure one way or the other because that's completely blocked. However, we're going to go with whatever can be justified. If it can be justified, then you are showing your learning. And let's look at letter C now. On the very top row, the very top layer, I only have one row at the very back, and that's 4 at the very back. In my second or middle row from the top, I have 2 here in the middle, and I'm going to make an inference saying that there are 4 in the back. Those 4 in the back, they would be holding up these 4. So I'm making an inference, and that would be 2 here, 4 in the back, and that's 6. So we have 6 centimeters cubed. And now let's look at our bottom row. I can see 4 here in the front. I can only see 1 here and 1 here in the middle, but something must be holding these up. So I am going to say 4 in the middle row and 4 in the back row. That means I have a 4 by 3 in my bottom layer here. That's 12. So I have 12 centimeters cubed. And once again, our sum would be 4 plus 6 is 10, plus 10 is 20, plus 2 is 22 centimeters cubed, like that. And we're going to move on. And these ones here, you are free to use a formula and a calculator. A reminder for this unit, I'm not looking to see if you can do all the mental math or all the paper and pencil work. You are completely allowed to use a calculator or use mental math or paper and pencil. So the formula for finding out the volume of this rectangular prism is simply length times width times height. Make sure you take the correct dimensions. So we have 5 centimeters length this way, 4 centimeters this way. That means the area of the bottom face is 20 centimeters squared, but we also have a height. So 20 times 3, that means we have 60 centimeters cubed because we make this with cubes. Each face can be made with squares, but the structure, the prism, must be made with cubes. And now let's go on to B. 40 times 30 times 1. Using mental math, we can say 4 times 3 is 12, and then add the zeros. So that's 1,200 centimeters cubed. And now for C, we can say 5 times 5 times 5. 5 times 5 is 25, times 5 is 125 meters cubed. Number 4, how many faces does a cube have? So we can see 3 faces on this cube right here, but each face here is directly opposite from another face that we cannot see. So this top one is opposite the one on the bottom, the one on the right is opposite the one on the left, and the one at the front is opposite the one at the back. So there are 6 faces on a cube. how many faces meet at each vertex of a cube. So, a quick reminder here, it's one vertex or many vertices. So this is a vertex right here where the lines meet, and we can see from this cube, and for every other cube for that matter, that we have 1, 2, 3 faces that meet at this vertex. And let's take this vertex for example. We have one face, two faces, and the face underneath that is visible from, it's not visible from here, but it would only be visible if we lifted up this cube and looked underneath. So there are 3 faces that meet at each vertex. That was our review for this unit. Please make sure, grade 6, you understand all of that before you start. This will help make it go much more smoothly. Thanks, everyone. Have a great day.